So World War I served kind of as a demarcation between the first generation of quantum mechanics and the second generation. And that happens. And by the time 1920 odd rolled around, we were fully 20 years removed from Planck's work, and that's a full generation of young scientists. And so anyhow, it was time for new thinking yet again. And this led to one of the more interesting characters that showed up in this little story, Louis de Broglie, who looked at the world a different way. This is his only significant contribution to the science of physics, but it was very powerful. And the cool part about his work is he uses very simple equations. It isn't about the mathematics in particular, it is how it is perceived. What is it telling us about the universe? If you interpret your mindset differently, what does it say? And I think that's a really powerful piece of work. And this led, of course, to this duality where matter can show wave and particle character together. And this was the first time that that was really shown. We had harbingers of it in work before. So anyhow, that's where we're starting. And of course, some of the extensions of his work where it was verified in the labs and so forth.
So as the war ended and into the 1920s, the young French aristocrat was raised by his older brother, Louis de Broglie. If you look him up, he's got a lot of extra names. I guess aristocrats can afford them. Anyhow, he had a really interesting idea because he looked at nature a little differently. Now, if we back up our little clock 20 years and we look at the photoelectric effect, and we see a massless electromagnetic light effect hitting a piece of metal and knocking an electron out. Now this is an electron, of course, is a piece of matter. It has mass, and there is a principle called momentum, mass times velocity, and you can't change momentum without like a collision, if you will, without the other particle having some mass. So here is a light particle, which we call a photon, behaving like a physical particle. So you see a case, and then of course the photon itself is really not a wave any longer. It is a particle, if you will, of light. So he was seeing this symmetry. The photons clearly have wave properties. We've been seeing those for a long time. And at the same time, we're seeing the particular properties. Okay. Now, to paraphrase a little bit here, of course, but now you look at matter, let's say electrons or something like that. Now, would they not have an attendant wave function? Would matter be symmetrical? And so, like a lot of things, you get this idea, and then you start looking at, let's just go way back to Newton. I mean, here, the apple falling in his mother's orchard, and he looks up at the moon and sees it sitting there, and connected that the two things were affected by the same force. So de Broglie's looking at nature and wondering if this symmetrical is reciprocal. Let's have a look at what he did.
As the war ended, a young man named Louis de Broglie, whose older brother, who had raised him, was involved in physics, and Louis wanted to contribute, and he needed an idea. He had seen in nature that there was symmetry between plants and other materials, and he began to think about what he'd already seen in quantum mechanics and in the structure of the atom, and whether or not that there was an argument for symmetry at this level. So he said, well, first you have photoelectric effect, and you have electromagnetic radiation giving momentum to electrons. And electrons are massive objects. They're not in the sense of being heavy objects, but they have mass. And momentum is defined as mass times velocity. So typically, something that has no mass, like radiation, cannot add momentum, but yet it did seem to do so. So if a wave then has particle behavior, and we also noticed that photons are effectively particles of light, if all this is true, then could a particle have wave character? This was kind of the question he asked. Now, to his credit, he didn't pull out all kinds of exceptional mathematics. He didn't have to. He took four equations that we already, in many ways, are familiar with. Equals mc squared. Planck's equals hf. The speed of light is equal to the frequency times the wavelength. And we have the momentum linear momentum is equal to mass times velocity. Now, none of these equations are difficult, and they can all be seen in high school textbooks. It is the interpretation that is genius in this case. So let's start off with, okay, so how can electromagnetic radiation have momentum? We said momentum is P equals mv. Said, okay, well, let's see what we can do with this. He said that P is equal to mv. Then he said, okay, E equals mc squared, which implies that the mass is equal to E over c squared. So then he would have momentum is equal to E over c squared times v. But of course, this is really, v is simply c. And so you end up with E over c. Now this isn't a comfortable equation, so then you add a few other things. We have E is equal to hf, which is equal to hc over lambda. So now we have P is equal to hc over lambda c. Cancel the c's, and we get h over lambda. And that was his equation. And this worked. You could employ this with the photoelectric effect and get the momentum that you were imparting. So it was pretty amazing, knowing the wavelength of the incident radiation. So this was one of his first, one of the first things he came up with was, of course, this whole notion of, but he didn't stop there. He did a few more things. So let's look at those. If we look at the does matter, have wave property. You have to appreciate that in many ways this is not expected. It's not observed by eye. So no one was even thinking about this. So he said, okay, well, all right, let's take the wavelength then of a, we'll start off with something basic. So let's take a baseball. Okay, and we all know it's hard to hit a major league curveball, so maybe the reason they're missing is because of diffraction or something. Okay, at least it's a theory. So we could say, well, the wavelength of a baseball is going to be equal to h over lambda, sorry, h over p. And this is equal to h over mv. This is equal to 6.6 e to the minus 34 divided by, say the mass of baseball is 0.2 kilograms times, we'll give the reasonable, we can say 40 meters per second if we want to be bold about this. Okay, and let's see what we get here. So when we calculate this, we get 3.3 times 10 to the minus 35 meters, which is ridiculously small, and so we never observe it. So if a major league hitter can't hit a curveball, it's not because of diffraction. Okay, so we need object with less mass. So we'll choose an electron. So the wavelength of an electron then would be exactly the same calculation. We'll go right to hmv here, which is equal to 6.6 e minus 34 divided by, now the mass of the electron is 9.11 times 10 to the minus 31
times. And its speed in a room, typical room temperature, is about 100 kilometers per second because of thermal agitation. So it's fairly high. And let's see what our calculator tells us. So we calculate this. In this example, we're going to get 7.3 roughly times 10 to the minus 9 meters. That's something we can measure. So then the idea was electron diffraction. And this was found both in the United States at the Bell Labs. So we have the Bell Labs with Davison and Germer. And
in our earlier studies, we looked at single and double slit diffraction and the effects that it created. However, when we get to something like an electron, where the wave length is predicted to be so much shorter, almost 100 to 1,000 times less, a slit like this is no longer adequate. And so what physicists decided to use was actual crystals themselves. So here's an example of a crystal lattice like you might get with table salt. But of course, we can have various different kinds. And as you orient the crystal, as they learned also with X-rays, is the spacing between the atoms provides you with the type of diffractive slit, so to speak, that is necessary to generate the diffraction pattern. And we'll see this here with electrons, and what you'll also notice is the different patterns you get as a function of the type of crystal lattice. And so this, of course, also allows us, just like with X-rays, a way to examine atomic or not so much atomic, but crystalline structure. And so that's a pretty neat effect in addition to that. You can also, if you position it differently, or you have a thin film, such was used by Thomson, a gold film, you can have rings, as we'll see in the next slide here, where you get the diffraction ring effect, more like you'd get from a point source. So either way, the diffractive effects of electrons were found fairly quickly. De Broglie published in 1924, and these effects were found fairly quickly, and they were exactly as predicted. So this was an exciting confirmation of this new approach to things that happened very quickly. One of the places where this diffraction effect was confirmed was at the Bell Labs. Now, I had mentioned earlier in one of my videos that after the American Civil War, that America began to become an industrial and technical giant. Now, certainly by the turn of the century and after World War I, this was certainly true. And America's wealth and ability to build, and its universities and so on, it became now very much one of the leading technical nations in the world, which arguably it still is. One of the facilities that came out from the genesis of the invention of the telephone and Alexander Graham Bell's fertile mind was this idea of a professional research lab, the first kind of which you could argue was started by Edison. But this one was done, again, mainly to invent new technologies and improve better ones, but to put a lot of capable people in one place, give them the equipment they require, and stand back. Now, just to give you a short laundry list of the accomplishments of the Bell Labs over many years, and you start thinking about the contributions this one institution has given humankind. The idea of sound films, where we had the sound and the video or the movies at the same time. Of course, we've got the diffraction of electrons. The beginnings of radio astronomy, the invention and design of the transistor, the C programming language, the charged couple device, which is at the root of all of our digital imaging detectors, solar cells, calculators, and of course computers themselves. Now, there were other people contributing, but there was certainly a lot of work done here as well. The design and the invention of the laser, and later the carbon dioxide laser, black and white television in the 1920s, and in between all of this, a very important device for all these technologies was the vacuum tube. Now, of course, there's a host of other ideas. These are ones that I hope that most of you would be familiar with. And Clinton Davison was one of the scientists who worked there. And he, along with Lester Germer, were actually going to use a beam of electrons and X-rays to examine the surface of nickel for its impurities and to see how if they could look at its improperties and how rough it was and so on. But they had cooked the nickel in the heat in an oven, and this, of course, changed its crystalline structure. And so as they moved their detector around, they began to realize that what they were getting, in fact, was a diffraction pattern caused by the surface being, in comparison, a lattice. And so in their example, it was more of an accidental discovery. And you can see here the apparatus where you have, and this of course is representation, but you have the nickel target and then the movable detector, and you're picking up the diffraction pattern that way. So Clinton Davison and along with later G.P. Thomson found that got the Nobel Prize in 1937 for this discovery.
Then in the UK by G.P. Thomson. Now it's amazing with G.P. Thomson because he's J.J.'s son.
The diffraction of electrons was also found by George Thomson, and amazingly George Thomson was J.J.'s son. And you see here the two of them around the turn of the century, and J.J. of course found the electron as a particle, and G.P. finds it much later as a wave function. So a remarkable family story in the as they developed the subject of physics. The Thomson family, of course, also is prominent in other areas, in diplomacy and other aspects, and well, Thomson's children also contributed significantly. And so quite a story. And Thomson worked at the University of Aberdeen, a grand old institution in Scotland, and where he came up with his device. But he went right after the idea of diffraction of electrons, heating electrons up to very high temperatures, of course, which creates higher speeds, and firing them through a gold film. So here's some of his apparatus at the university. He's the only professor, as I understand it, at this when this video is made, who has been given the Nobel Prize. And in his case, as I showed earlier, the diffraction pattern is for the most part circular because they're using a very thin film, and so you're not getting the same crystal type lattice. And of course, we're using gold, which is a much bigger atom as it is anyway. There's a nice picture here of Thomson's technical team. The gentleman who was his lab supervisor and equipment manager, so to speak, is sitting down, and there's the other helpers. And this, of course, is what happens with the Nobel Prize, because the Nobel Prize is given for discoveries and cannot be given to more than 3 people in a particular situation. So you have Davison and Germer, you have J.P. Thomson along with his graduate student, and so on. And all these people, I'm sure, worked very hard on these ideas. The Nobel Prize also is not given to people who have passed away. And so there have been people in the past who have been very deserving who did not get a Nobel Prize because by the time the prize was awarded, they had passed on. This can also be true for people who were discriminated against by their race or their gender. And by the time the world had caught up to these types of ideas, that person had passed away. And so there's a lot of profound discoveries in the 20th century alone, which were not recognized, shall we say. And then there's others that did very well. So it's just how it goes. And I think we have to always be a little bit careful with awards and so on. They're nice to have, and oftentimes the people who do win them are very deserving. But I think the thing we have to remember sometimes is that the people who didn't win them often can be extremely close and almost are very as much a contributor as the person who's recognized. And this is just how it goes. I think we should remember, though, that if you win a Nobel Prize, of course, this brings profound attention to your research, which can help everyone in that department, and often money. The Nobel Prize currently pays over $1 million. The one caveat to that, of course, is that you often win the Nobel Prize long after you've done your research. Sometimes professors today are recognized and they're in their 80s and are no longer performing research. But perhaps that money can still go back to the department or in a direction to support research upon which they're interested. But as they say, no system of recognition is perfect.
So this is a master stroke of work here, because even though the equations are straightforward, the implications are enormous. So he shows with small particles, in electron diffraction, it's now possible wave particles do exist. We can create diffraction effects, if we're careful, at this level, and they were found even as early as the early 1920s. And so we now have the idea of matter waves. And nobody has any idea what they would look like, because no one's even thought about that being possible. Now you have to understand that the initial group of researchers, what's their position on all of this? Einstein never accepted the probability aspects of quantum mechanics. Planck never even accepted really quantization in many ways, and so he never contributed again. Bohr became a profound teacher of quantum mechanics and had an institute in Copenhagen and so forth. And I think his true calling is in fact as a teacher. Sommerfeld was a tremendous teacher and had a great number of accomplishments that way. So did Rutherford. And so there was a lot of work done by the first generation, at least some of them anyway, as mentors and teachers of the next generation. But they weren't always happy with what the next generation did either, but that's okay. That's what's supposed to happen.
There's a final development that came out of the work of Louis de Broglie that was not originally expected. Let's retreat for a moment and go back to the work of Niels Bohr. Bohr, of course, had very specific radii or energy levels where orbits were permitted and where they were not in his original setup. But and although that worked, there was no explanation in the physics of the day as to why this was sound. If we move ahead now, roughly the 10 years to the work of de Broglie, we now have more insight. If we first look at the top diagram in this slide, we remember Planck's ovens and the idea of a standing wave. So if a wave is coming from the left to the right and it reflects and goes back, if the wavelength, if the length of the string, if you will, the distance between the two ends, is equal to an integer multiple of half of the wavelength, then you get this pattern, and it can have different numbers of nodes in it, but you still get this pattern, and it's known as a standing wave, as we've already talked about. What's happened is that the circumference of the allowed Bohr radii will equal the electron wavelength at that energy. So let's look at the diagram on the left, and if you see that diagram, you can see there's three maxima there, so that's 3 full wavelengths, that's 6 half wavelengths. So in this case, n is going to equal 3 because it's 3 full wavelengths. So what we're saying then is that the radius 2 pi r is what it is, and that will be equal to 3 times the wavelength of the electron's wave function that is allowed to be there. So this is why this worked out, because you have to have these integer multiples of the wavelengths not in between, and that's what sort of kind of in a way gets this quantization effect, which is what I kind of mentioned when we were talking about the ovens. If we look at the rightmost diagram, you can see that you have the one where there's 4 bumps, that is 4 full wave functions, so that's 8 halves, so this would be 2 pi r prime is equal to 4 lambda. But if we look at the other wave function that's not quite complete, it's out of phase. In this particular case, its wave length is not equal to an integer multiple of lambda over 2. And as a consequence, that one will be absorbed and will not be allowed to stand. And that would be an example of an energy that is not permitted. So although this is not the end of the story, it's certainly a very interesting development and adds to the whole notion of the wave effects and the wave character that goes with the matter that we talk about as an electron.
So here we have now this extension of the work of quantum mechanics, which shows that matter can be a wave and a particle in some way or other, kind of agreeing with both camps, if you will, in some respects. And so here's the beginnings of those ideas. And again, by this very clever interpretation of what are otherwise very straightforward equations. Thank you for watching.